So yeah, welcome to Applied Machine Learning. Today we'll talk mostly about very general stuff, introduction to what's machine learning and so on, and some logistics. This course focuses a lot on writing code and using existing machine learning tools, so we'll not really be implementing any machine learning algorithms ourselves, but it's more about using things like scikit-learn and Keras, so we are only using Python to attack real-world machine learning problems. And the things you have to think about, and the things that you need to keep in mind when you're doing this in practice. Can you hear me in the back? OK. So first for logistics. So most important one, my email is andreas.muller@columbia.edu. Not a Muller@columbia.edu. There's two Andreas Mullers at this campus, and the other one always gets my email. I think he's left now, so it's even worse if he still gets my email. So we have 6 TAs, or CAs, who should be here. Can you maybe stand up or raise your hand? All right, so we're going to announce the office hours for the CAs later. They're all going to be in MUT in the usual place. My office is in Interchurch, which is more or less across the street from here. It's like a little bit of a weird building. So I'm going to do office hours Wednesdays from 10 to 11. Oh yeah, so about enrollment. So as you might notice, the class is full. Actually, so there's supposed to be only 10 more people in this room than there's seats, but it looks like there's many more than this. So if you're on the waiting list, be patient. Maybe some people will drop out, but it's basically mostly full. If you want to audit the course unofficially, so without credit, you are free to sit in if there are seats, or stand in the back if there's not. I expect the next lectures won't be as busy. If you're a PhD student or a DSI student and you're on the waiting list, please email me. If you're neither of these two, please don't email me. I get 50 emails. Can I join your class? No, you're on the waiting list. This class is full. Sorry. So all the materials will be posted online and are available for everybody. If you want to audit and sit in, I can send you access to the coursework in Piazza for discussions. But maybe email me next week. But on the course website, which is this, you will find all the slides and also recordings. And if you haven't looked at the website yet, please do so. It has a schedule for the full semester. There's also the course website for last year, which you can look at, which has the schedule and all the slides for last year. This year will be quite similar to last year. There's going to be 6 programming assignments, which will make up 60% of your grade, and there will be 2 assignments, 2 exams, one before spring break and one at the end of the semester, each covering half of this, the lecture. So as I said, there's slides and course materials on the website. The slides that I'm showing right now are already online, and they all have slide notes. Hopefully they're not too outdated because they're mostly from last year. If you press P, you'll mostly see whatever I said. So you can go back and go through the slides. Usually I don't have a lot of text on my slides, but there's going to be the slide notes. Thank you. With all the content. I think off is better, maybe. Well, whatever. So for the later slides, I had the videos from last year transcribed and have them on the slide notes. So there's probably going to be some typos in there. So if you find any issues with the slides or the slide notes, please either send me an email or even better, send me a pull request on GitHub. All these slides and materials are all on GitHub, and you can send me a pull request. I'll be recording all of the lectures, and I'm recording this now. So ideally, I want to post all of these publicly. Probably this year they're going to go up on YouTube, but I don't have time to edit them. So if you ask a question, it might be that your audio will be caught, in particular if you're sitting in the front. And so I'll ask you to sign a waiver that that's okay with you as part of the first homework. Is there anyone who's not okay possibly being caught on mic? Well, either raise your hand now or say no on the waiver, but that means I need to edit the videos, which is going to take a lot of work and which I potentially can't do. So this makes it much harder for me to post the videos. But yeah, everything will be recorded and posted both on the website and probably on YouTube. I had a lot of issues with plagiarism in the homeworks in the last semester, so I just want to make this very clear. So I use automatic code duplication tools to check for plagiarism in the homeworks. If you copy and paste other people's homeworks, both of you will get 0 points. You can feel free to copy and paste from my slides or use Stack Overflow, use online tutorials. If you use online resources, please acknowledge them. If you use my slides, just that's fine, don't worry about it. But if I see that your homework was turned in by someone else as well, 0 points. Another question I always get is, everybody wants to do a project with me. If you want to do a project with me, the best way to get my attention is start developing and contributing to scikit-learn by yourself. There's a very comprehensive developer's guide, and there's lots of issues, and you can go on there and you can start fixing issues on the issue tracker. There are things, easy issues to get started and so on. So if you want to do a project with me now or later, start working on scikit-learn yourself, and if you did some cool contributions, I'm happy to work with you and do some more in-depth stuff. A couple more things about other resources. So there's suggested readings on the course website. These will mostly be from the first two and possibly the third book. So the first book is obviously the book that I wrote, and I'll probably post a PDF on Courseworks for this. Please don't share the link. This code is not available for free because I wasn't that generous yet. The second one is also a very good book by Max Kuhn, Applied Predictive Modeling. It's actually written for R, but a lot of the things in there are language agnostic, and they're highly recommended. The third one is less applied than the first two. So my book has no math on purpose. And this class will be quite a bit more advanced than what's in the book, but it's still a good resource to get started. The third book is only math, no programming, and so it's not very applied, but it's good for some background reading. It has also the benefit of being available free online on the author's website. And I think it's a pretty good introduction. If you haven't taken a machine learning course, or if you're taking a machine learning course right now, this is a good book for the more theoretical parts. There's also a book called CIML by, I never know how to pronounce his name, Hal Dom III, I think. It's also available online. It's like an online book. It's in between the two. And I think it's what the DSI course uses right now, the DSI machine learning course. In terms of more on the Python side and like data munging, so I said the prerequisites for this course are about what's in the Python Data Science Handbook. If you're not familiar with it, the Python Data Science Handbook you can also get online for free as Jupyter Notebooks. It's written by Jake Vanderplas. It's great. It talks about Matplotlib, Jupyter, Pandas, NumPy, and so on. So these are all things we're going to use. We're going to talk about Matplotlib a little bit next week, but I mostly assume you're all pretty familiar with Python and with the libraries for like doing basic data munging. If you're not, check out the Data Science Handbook. All right, so that was all for logistics. Any questions about logistics so far? All right. So now I want to give like a very high-level overview of what is machine learning and what we're going to do in this class. We'll get down to the metal very quickly, even later today, but this is going to be first a very high-level overview. So what is machine learning? So to me, machine learning is really focused on making predictions. And this class will have a very heavy focus on making predictions. So you learn from a data set of given inputs and outputs, and you want to predict for new data what would the output be. So this is in particular supervised learning, which I'm going to discuss in a little bit. And this class will mostly focus on supervised learning. First, I want to give some examples of where you see machine learning in your everyday life. It's very possible that most of you are using some machine learning right now, or someone else is using some machine learning on you right now. If you look at things like Facebook, if you look at any of these sort of more advanced websites, there's many applications of machine learning wherever you look. There's one thing that shows what to prioritize in your timeline. There's another thing by this company that shows who should they show an ad to. Then there's a thing that at Facebook that says which ad should we show and how much should they pay for it, for showing it to this user. There's machine learning algorithms for who I want to connect with, who I might know, what trending things to show me, which birthdays to show me. So there's probably around like 10 machine learning algorithms whose output is shown in this page. And if you look at more, like if you click on the picture, this is me with another couple of core developers of scikit-learn. So it automatically does face recognition, which is again machine learning. So here it shows only the faces that are detected. I'm pretty sure they're able to know who the people in the picture are, but because of privacy concerns, they don't tell you, but they know. They also know that it's a conference, and they probably know a lot about this picture. And again, they show some ad that I think is relevant. And all of this is done with machine learning again. Yeah, I don't want to spend too much time, but there's machine learning in places where you might not even expect it. For example, here, so Amazon has a lot of machine learning clearly to like prioritize. If you type in machine learning, what's going to show up? This is a ranked list learned by machine learning. There's also a machine learning application that says what ad to show in the, at the very top. But there's also machine learning on like this page, for example. There's a machine learning algorithm that shows what price to show. There, like Amazon doesn't adjust the price for you, but it adjusts which seller to use. And here, for example, this is probably shipped and sold by Amazon. But also there's many other people that sell it on Amazon, and so Amazon has a machine learning algorithm to say which seller should I show as the prominent seller. Again, ads, obviously, then things that are bought together, and then what is the format that this user should be shown to. So should I show the Kindle version first or the paperback first, or should I show the used one first or the new one first? And so again, there's like so many machine learning algorithms whose output you can see in this single page. So if you look at any web application that's like more complex, there's machine learning everywhere. It's probably, if you use the camera on your phone, there used to be one algorithm, which is the face detection, but now there's many more algorithms for focusing, for like blurring, for deep blurring, for all kind of things, for changing styles, and most of these work with machine learning now. So most of you are probably going to go into industries, so sort of web data is one of the data sources that a lot of people work with. I know that a couple of you are scientists, and so there's also many applications in science. So I don't want to just focus on sort of these industry applications. This is an application I quite like because it has a nice picture. This is what a friend of mine at NYU used to do. He detects exoplanets. So this is planets circling around other suns, and this is like a nice artist depiction. The problem is if you have a telescope, the whole other star is a single pixel. And so this whole thing would be a single pixel. And the way to detect whether there's a planet is if there's a periodic change in brightness that corresponds to being a shadow of a disk. So you can say if the planet goes in front of the star, then it casts a shadow, and so the star appears less bright. If there's a periodic pattern in that, that matches sort of the physics behind it, then you know there's an exoplanet. So you can't actually see the planet, you can only see the shadow it casts. But there's obviously many, many more applications in science. Like, for example, in genetic, medical diagnosis, behavioral sciences, like basically everywhere where there's data, there's applications of machine learning. So I already mentioned supervised learning, but I want to go through generally the types of machine learning we want to talk about or what is out there. So there's three sort of fundamental types of machine learning: supervised, unsupervised, and reinforcement. This class will focus mostly on supervised learning, we'll do a little bit of unsupervised learning, and we'll do none at all of reinforcement learning. So what are these three? Supervised learning is very related to, say, function approximation. The idea here is that there's some underlying process that governs the world that we call P of x and y, where x is a description of some object, let's say a user that visits your website, and y is an outcome of interest, say whether they click on an ad or not. And there's a joint distribution of all the users and whether they click or not, and this is sort of the world, and it's captured in this P of x and y. So this x is usually a vector of descriptions of, say, your user with age, how often they visited your website, where they're coming from, how long they've been online, anything you can think of. And let's say y here would be they click on an ad or no. We assume usually these are drawn IID, which means independent and identically distributed. So we assume all of these that we observe come from the same distribution, and they're all independent. So there's no like groupings, or there's no temporal aspect. In real applications, that might not be the case. Like the way users behave might change over time, or you might collect it only certain users, not other users. But generally, the assumption supervised learning is that all your data points are created equally. And the goal is to find some function for which, given the description of our user xi, we match the output yi for some observed training set. So this I are sort of several observations that we collected. We have both the description of the user, whether they click the ad or not, and we want to fit a function that, given the description of the user, gives the right output. I say basically approximately. So here, if it's a yes/no decision, you would say it usually does the right decision. This is basically function approximation. And what we also want is that not only for the data which we collected, we know that f1 xy is approximately yi. We also want that if we draw a new point from the same underlying distribution, so if we collect new data, this still holds. So for a new user that visits our website, we want to be able to apply the function and get the correct outcome, be able to predict whether they're going to click on the ad or not. And this is called generalization. And so this is, in a sense, the goal of supervised learning is to find a model that generalizes well. You're not really interested in finding something that makes good predictions on your training data set, which is the data for which you already know the answer. You want your model to be able to give you answers where you didn't have answers before. And this is what we're going to talk about in depth for basically the rest of the semester. Some examples of supervised learning are spam detection, which is probably one of the first examples where this was used in practice commercially. Given an email, is it spam or not spam? So first, to do this, you need to collect a set of emails, have users annotate them. Are these spam or are these not spam? Given this user annotation, you can then build a model. And then once you observe a new email, the model will tell you is it spam or not, based on the training set that was annotated by humans. Another application, medical diagnosis, or assisting in medical diagnosis at least, is, here you would have patient data and collected together with the diagnosis by a doctor. Let's say for one particular thing, does this patient have diabetes, yes or no? Again, you would use the human expert here to annotate or to diagnose your training set, your patients, and once you have these diagnoses, you can use the model to make predictions for a new patient, saying, does the model think this new patient has diabetes or no, yes or no? Usually in this setting, you don't want the machine learning algorithm to make automatic decisions really, but you can use this to screen for patients or to assist doctors in their assessment. For example, if the machine learning algorithm is very sure that the patient is healthy, maybe there is no point in them seeing a doctor. If the machine learning algorithm is unsure, maybe it's better to send them to a doctor once too often rather than missing a sick patient. And I already mentioned at-click prediction. So here, basically, you would observe users on your website over time. So here, there's actually not really human annotation. There's you just observe what happens. You observe users. They behave a certain way. And given this record of the past, you can try to predict for the future, will a certain user click on an ad, yes or no? All right, so the second category is unsupervised learning. Again, usually you have this assumption of data being collected IID from some underlying distribution. Only now there's no Y, there's no outcome here. Let's say we just have a collection of users on our website. And we assume they're drawn IID, that we collected them. And now the task is learn about the distribution P. This is a very vague task in a sense, because it doesn't really say what the output should be. And there are several subcategories of unsupervised learning, say clustering, where you try to group data, or density modeling, where you try to explicitly model this probability distribution, or dimensionality reduction, where you want to compress the representation of your data while maintaining most of its properties. But generally, for most of these, it's sort of a little bit hard to define what the actual goal is. And so these have a little bit less use in practice. At least not as the main application. These are often part of a supervised learning pipeline. And the last thing I want to talk about, or the last kind of machine learning, is reinforcement learning. This has got quite a bit more attention than before in the last 2-3 years, because there was this big success of AlphaGo beating the world's best in Go, which people thought is still years out, but I think it's 2 years ago now that basically they built a machine learning algorithm that just via self-play learned to play Go at better than human level. So reinforcement learning doesn't work with a given data set. It's about an agent interacting with an environment. So in this AlphaGo case, it is the environment is the board, including your opponent, and the agent takes actions, which is placing the stones. Another example could be a robot interacting in an environment, navigating through a room, trying to find something. Or An application that many people think about right now is self-driving cars, where the environment is basically the whole world or the network of streets, and you have the car as the actor, and the car tries to make decisions in this environment. These are all driven by a reward function. In the playing Go, it's probably like win the game. So if you win the game, you get a reward. If you lose, you don't, or you get a punishment. There's no instructions on how to win the game, just if you arrive at this goal, it's good. Similarly, for a self-driving car, the goal might be get to where you're going quickly and safely. And if you achieve that, that's good. If you crash and kill your passenger, that's bad. And but again, there's not really instructions. There's only the agent learning from experience. The main reason why this has not been very successful is that this often requires a lot of trial runs. So this Go player learned by playing itself millions of times, which works well with a board game. It also works well if you have a very good simulation of what's happening, which is why you can do this with video games as well. Because you have an environment in which you can have the player play again and again and again. If you have a robot or even a car, you don't really have a good simulation of your environment. And because you need to do this thousands or millions of times, you can't really do this in the real world. You can't have like a million self-driving cars crash before they learn how to drive. Even if it's not as like drastic as crashing, if you want to do this with just a robot learning to walk, the person that like had to set up the robot, reset it every time it fell down, or has to change the batteries or whatever, will like probably go crazy before the robot learned anything. And also, all the joints will wear out, and the robot will change before it starts to learn anything, because it has to use so many trials. And so this is why there's like not that many real-world applications right now, unless you have a very good simulator. And there's definitely a lot of progress, and I'm sure like things will get better soon, but this is the main obstacle right now, I think. So yeah, we're not going to talk about reinforcement learning at all, because, as I said, it has like not that many real-world applications yet. There's other kinds of hybrid types of machine learning. There's semi-supervised learning, where you have the output Y only for some of the samples. There's active learning, where basically the algorithm learns to ask for labels for interesting data points. So let's say most of your data is not labeled because labeling takes a lot of effort or money. Say diagnosing a patient is very expensive, or there's some very elaborate human annotation you need. Then it makes sense to only annotate data points that are interesting for the algorithm. And so in active learning, you learn which data points to annotate. And of course, there's forecasting. This we're actually going to talk about a little bit, which is one of the types of data that's not IID, where you have a time component. So I had this in here for like the last 2 years. This is the motto of Yann LeCun, I think, who is a very famous researcher at NYU and Facebook, and is part of sort of the people that worked on deep learning things for 25 years, 30 years, over 30 years now. And he says, the revolution will not be supervised. And I usually have said, this is not really true. Most of the applications in machine learning, or this is not true yet, most of the applications in machine learning right now are supervised. So they require human annotations, both to learn and to evaluate. If you look at the breakthroughs in image recognition in the last couple of years, they were all driven by supervised learning using the ImageNet data set. annotating this very big data set is what made a lot of the breakthroughs possible. But actually within, I think, the last year or so, there's been a lot of breakthroughs in NLP in a similar way that actually used unsupervised learning. And so there's things like Elmo and BERT, which we'll discuss later in the semester, which use large text corpuses and extract representations of the data in an unsupervised way that are much more semantic than what was available before. And so the main idea behind this, the revolution will not be supervised, is that it's very hard often to annotate data. And you often need human experts. And so this is a bottleneck, having the annotated data. But there's so much data out there. There's basically infinite amounts of text out there. So if you want to learn something about text, you should be able to use this text in some unsupervised way without human input. And so this has been like a motto of some researchers for many years. Now this at least came partially true in the text area. And I'm sure we'll see more people using unsupervised learning in other areas. Now I want to come back to supervised learning. So there's two basic kinds of supervised learning. This is the main things we're going to talk about, classification and regression. The difference is basically y being discrete or categorical, or y being continuous. So a classification question will be, will you pass the class? And a regression question might be, how many points will you get in the exam? The difference is that for classification, there's discrete choices. Here there's two choices. So it would be a binary classification setting. And you want to make this exact prediction, yes or no. Whereas in regression, there's a continuum of possible answers, and as long as your answer is pretty close, you're mostly happy. If I want to predict someone's salary, and I predict like, let's say, $101,000 a year, instead of $100,000 a year, that's not really that big of a difference. So it doesn't really matter what if I made the exactly right prediction. Whereas in classification, all the different outcomes are like completely independent, so I need to really make the exactly right one. Usually it's relatively clear which of the two you're looking at, but there are some cases where it's not entirely clear. For example, if you have like a 5-star rating system and you want to predict how many stars will this restaurant or this movie get, there's reasons to frame it in either way. This seems like a little bit of an odd distinction, actually, I think, from a mathematical perspective, because they are very similar in all other respects. But the difference is how we measure whether a prediction is good enough or not. And so we need quite different algorithms, because we measure whether a prediction is good in very different ways. Slight sidebar that I always get, because who here is from statistics? Anyone? Oh, either you're very shy or there's less people than usual. So often people ask me about, so isn't this all of this just statistics? And so I want to make some very broad sweeping statements that are completely false. But in my mind, statistics is usually about inference. So statisticians care about often answering a single yes-no question. Let's say, I don't know, who will win the next election? It's maybe not a yes-no question, but there's like multiple outcomes, and you want to say which one is the right outcome, but it's a singular event. Or if you want to say, is this drug effective or not? It's a single outcome that you want to predict. And often you also want to understand the mechanism. Why does this happen? What is the cause? Whereas what I'm interested in here is just prediction, where we have many, many data points, and we want to make predictions for individual data points. I don't want to know whether the drug is effective. I want to know, will it work on this patient, or will it work on this patient, or will it work on this patient? And really, the boundaries here are very vague. There's definitely people in machine learning that do inference, and there's people in statistics that do prediction. But this course will be mostly about prediction, and I care much less about inference. And so as long as I can make good predictions, I don't care that much about what the model is, or if the model is realistic, or if the assumptions of the model are met. As my measure of goodness is, am I able to make good predictions? Is my model able to generalize well? If my model is able to generalize well, I'm happy. If it doesn't, I'm unhappy. If you want to do inference, you have very different criteria. So, actually, how long is the lecture? Is it until 30 past? 35 past, right? Can anyone confirm? 25? Okay. All right, so I want to zoom out a little bit more even again and talk about some general guiding principles in machine learning before we're going to dive in next time. There's a lot of people that sort of see machine learning as a cure-all, and I want to prevent you from seeing it that way, and also want to prevent you from trying always the fanciest algorithms first. So the first thing I want you always to think about when you encounter any problem is to think about, what is your goal? Your goal in your real life situation, like at a company or in your research, your goal is never to classify something correctly. You never care about whether you'll predict if the user clicks or not. Arguably, you also don't care if you like what your accuracy is in diagnosing a patient. There's usually a goal behind this. There's like, you want to make money with ads, you want to like cure patients, you want to prevent an outbreak, you want to find better drugs. So there's always some like real world goal, and the real world goal is never measured in like accuracy or F1 score or something like this. And so this is the first thing you should always think about, is what is your goal and how can I measure this goal? Oh, I just realized this is not the right. Okay. And usually you cannot measure this goal directly, but you can measure some proxy. Maybe this proxy is accuracy, but it's not really the real goal. If you're in industry setting, often you can say, well, if I predict well, how much money will I make? If I predict badly, how much money will I lose? And you can say, deploying this solution or this algorithm will make me so much money, whereas this other algorithm will make me so much money. And this might be the goal that you actually care about. Or this will engage users this much, this will engage users this much. So you want to stay as close as possible to what your original goal is, though usually you can't measure that. As a company, maybe it's have happy users, but that's very hard to measure. Then, so let's say you know what your goal is. So I would argue you should often try a data-driven approach, but not necessarily machine learning approach first. So think about, how do you measure success, and then come up with the simplest thing possible, which is maybe like a single if statement or anything like that. Then evaluate how well does this do for your ultimate goal. using machine learning systems, in particular, using very complex systems, has a lot of hidden costs in terms of complexity, in terms of maintenance, in terms of understanding what's happening, unforeseen consequences, software to maintain. So don't start out with like the most fancy machine learning algorithm you can think of. Use the simplest baseline that you can think of first. Maybe say every patient is healthy, and then what is the benefit of improving over this baseline? What is the real world outcome that I get from using a more complex solution? You should also not only trade off like how much more will I get with a more complex solution, but is that worth your time? Usually, using a more complex solution is not free, even for now. Like, just deploying it takes a lot of time for you to investigate. So is it worth to spend a lot of time tuning your neural network if logistic regression works just fine? If you get 1% more accurate, how much more money will this make you? Versus, what if you spend your time working on a different application that might be much more impactful? In industry applications, what I very often see is that people are very new to using machine learning at all. And so the main problem is not like creating the most fancy, the most accurate machine learning algorithm. The problem is usually identifying what is the problem, finding a measure, and then deploying the simplest solution that you can think of. And this will be like 100 times better than whatever they did before, because people didn't even measure what it was they care about. Once you did that, you should move on to the next simple thing, because you get like 100x in the next simple thing where you introduce machine learning compared to like a 1% improvement if you really polish this one thing. So this is what I see most in real world. If you're in a place where everything is already highly optimized, if you're like at Google or Facebook, that's not the case. There, they already squeezed out as much as they can, and every single like fraction of a percent matters a lot. Similarly, in finance, you often care if you even slightly better than chance, you can make a lot of money. But outside of these areas, usually just deploying a simple solution and moving on is better. Another thing that's quite important and that people neglect is communicating results. So as I said, what you care about is never really accuracy or F1 score or average precision or whatever you're measuring. And so if you try to communicate this to your boss in this way, then they will like have no idea what you're talking about. So not only should you think about what are the actual real-world implications of what you're doing, you should also be able to communicate this very well. And phrase your results in the language of the actual application. All right, so I think that was all sort of on general machine learning guidelines, and but I can't really emphasize this enough. I had a lot of people every year in my capstones, which I used to teach in the fall. They took my class, and then they still didn't do this. So maybe I should do this again in the end of the semester and tell you, always use the simple solution first. I have people working for a month at like some fancy neural network, and I tell them, use linear model, use a linear model, use a linear model, and then last week they use a linear model and it's much better. And they get carried away with trying something that looks cool and fancy, and but they don't build a baseline. Always build a baseline, even like the constant baseline. A lot of people don't compare against the constant baseline, which is quite silly. All right, so there's two more related things I want to talk about that you should keep in mind when doing machine learning before I switch more to talking about tools. So I said I basically only care about prediction. However, maybe my users care about results, about why predictions were made, or my manager cares about why predictions were made. In some settings, making a wrong prediction is pretty bad, or you need to justify why you made a prediction. And having explainable results usually makes people trust much more. If you look at, here in this case it's Amazon, but you also have that at Netflix, for example. It tells you, I recommend this to you because you did this. You watch this show, so why don't you want to watch this? And it's been shown that people trust this much more. This can also be helpful for you debugging a machine learning algorithm. If your algorithm makes a very bad mistake, you might be able to figure out why it made this mistake, if you can explain why a particular outcome was happened. Interestingly, the explanations don't need to be real for it to have an effect on your users. So if you want, you can train an algorithm to make predictions, and then you can train a second algorithm to come up with explanations that have nothing to do with the actual predictions. And if they're plausible enough, your users will also be happy. Some might argue you're lying to your users, which might be correct. I don't know, but it's quite interesting, and I think there's like some interesting questions there because people also make up explanation post hoc. If I ask you where you go for lunch, then you give me something, and I ask you why did you go there for lunch, you're going to make up a reason. And this reason is not actually why. You have no idea why you made this decision, but you can probably justify it in some way afterwards. I think that's like how humans mostly like give explanations. But I think if you do this for machine learning algorithms, people are kind of skeptical. This relates to another topic that has gotten a lot of attention recently, which is ethical considerations in machine learning. If you haven't read this article, it's quite interesting, and it sparked a giant discussion. This is a ProPublica article, I don't know, it's probably like 3-4 years old now, about risk assessment bias in a system called Compass that's used in the criminal justice system. So here, you can see 2 petty theft arrests. Or maybe you could see, can someone turn off the light? Like the front light? Is that possible? Well, I think, so right now you can see that Vernon Prater on the left has prior offenses, 2 armed robberies, 1 attempted armed robbery, and 1 grand theft. And Brisha Borden has 4 juvenile misdemeanors and no subsequent offenses. And the person on the left is classified as low risk by the system. The person on the right is classified as high risk. If the lights were turned off, you could see the reason why. At least the reason this article claims why is the person on the left is white, the person on the right is black. So the article looks at the system and says there's a racial bias in assigning much higher risk to people of color. And then there's like a really big follow-up conversation on this, pretty big controversy about is this actually a biased system, yes or no? And it's actually quite hard to say, is a system biased, yes or no? There are several criteria for fairness that are actually mathematically conflicting, which is interesting. So there's like, I don't want to go into this too much detail, but if you're interested, you can look this up. There's like basically 2 main lines of thoughts of what constitutes fairness, and they're impossible to meet both, but both sound completely natural. And so this is like quite tricky. This also plays into the explainability. One of the issues with this algorithm is this is a company that they give this to the courts, and it's completely unclear what this algorithm is. The public doesn't have access to the training data, doesn't know what model it is, doesn't have any access to the algorithm, so that doesn't really inspire a lot of trust. And one might argue that if you use a system like this in a criminal justice system, you should at least like publish your model. A friend of mine works in finance. Interestingly, in finance, the controls are much stricter than here. And whenever she changes her model to detecting whether anyone is doing something fishy, she needs to file basically an application to the SEC, I think it's the SEC, which has the coefficients of your logistic regression printed out, and they need to sign off on this before she can use the model. So, so in finance, there's actually a lot of regulation. Here, not so much. And so, yeah, so I want you all to keep these ethical considerations in mind when you go out in the world and do machine learning. Particularly if people are involved in any way, there might be quite bad biases, and you hear stories about this all the time. But there's not only a bias in the algorithm in some sense. Often, the ethics is also in the application. There's an example from the book called Weapons of Math Destruction, I think. Math as an M-A-T-H. Where basically two schools have similar algorithms in place to predict if students will underperform. And so they take all their scores and like their social interactions, whatever, everything they have about the students, and they figure out if they underperform. One of the schools gives the people that they predict to underperform additional mentoring so they can improve. The other school uses the same model to kick out these students before the evaluation period so that their evaluation scores are higher. So no matter what the model is or how biased it is, clearly one of them maybe is a better or more ethical approach than the other one. One of the main things about ethics is also in how you collect the data, and of course it's very easy to get biases. Most commonly, biases in algorithms come from how the data is collected. Pretty recently there was a story about Amazon scrapping their automated hiring tool because it only hired men. And because it said men are always better. And one possible reason why this might happen is because there was such a strong hiring bias in the past. I mean, it's been shown there's hiring biases, in particular in tech, a lot. So people prefer to hire men. And so if in the data that you collected, your historical data, this is what happened, then this is what you will basically learn. Another example of this is predictive policing. So there are some cities that use machine learning algorithms or have some experiments trying to use machine learning algorithms of where to send cops on a patrol. The point is, wherever you send cops, they'll find crime. So, and traditionally, they usually go to black neighborhoods. And so if you keep sending them there, they'll find more crime, because wherever they go, they find crime. And so what you'll learn is to keep sending the police to black neighborhoods, because every time you send them there, you find crime. But this is just because of the bias of previous decisions to go there, that your data collection is biased. One second. Another interesting ethical aspect of data collection is that if you want to make sure your algorithm is fair, you actually need to collect the data that you don't want to discriminate on. If you want to be fair with respect to gender, to ensure you're fair with respect to gender, you need to collect gender as so you probably don't want to include it as a predictor in your model, but you want to collect it so that you're able to ensure your algorithm is fair. All right, but aside from the ethical consideration, data collection is usually a main issue in all data science, particularly machine learning, because that's usually the limiting factor in any applications. And I want to talk about very briefly something I slightly mentioned before, which is free versus expensive data. So sometimes you can get labeled data for free. Usually this is if you want to learn from the past and predict for the future. So, for example, if you want to predict the stock market, it doesn't work. But in theory, your training data is just the past stock market. You know, you can see how stocks developed. You have the history of the world, so you know what the output is. As I said, for ad clicks, you can just log what your users are doing, what products they're looking at, what products they're buying, and you will get this information, and so you will have the target variables. If you're very smart like Google, you can also get house numbers labeled for free. But that's not typically what happens. So Google was very smart, and in creating reCAPTCHA, which you probably all know, where to validate you're a human, you need to enter some house numbers. They use that to train their computer vision algorithm. Right now, what you probably have to do is find the parts of a picture that have a storefront in it or a car. Guess what they do with that? So this is data that often, like, if you predict observable events, you can often get a lot of data. However, I mean, there might be issues with this. For example, people never click on ads. So if you have ad impression data, maybe 1 in 100,000 will be someone that actually clicked. So that might be a bit of a problem. But at least you can get basically infinite data for free. If you want to automate a complex process, a human process, that's usually much more expensive to collect data, and data is much more valuable in a sense. For example, medical diagnosis requires a human expert to do a diagnosis. If you want to know whether a particular molecule will be a good drug, you need to produce it. You need to run a drug trial. This will take years. So basically, saying whether this one molecule, is it good against cancer? Yes or no. For a single label, you have to invest millions. Similarly, for chip design, if you want to say, oh, is this computer chip going to be effective? How hot is it going to get? How much power is it going to consume, and so on? You need to actually manufacture the chip, which is, again, this is a very complex process. Then you need to measure it, and so on. So, in a sense, you can save a lot of work and money by automating these processes, but collecting data is very expensive. And a lot of people come with me with, I have this great machine learning idea, and that's gonna change everything, but I don't have the data. But the data is usually a thing that is the hard part. In particular, having here, so what is expensive here is getting the labels. Again, coming back to the theme of supervised versus unsupervised, if you want to do supervised learning, you need to have the known outputs, and they might be very expensive to obtain. Another thing about data is that there might be a lot of data, but you might not need a lot of data at first. I've seen a lot of people spend a lot of time working on data pipelines and setting up a Spark cluster and, wait, do I have this? No. And doing very complex things before they even ran a simple baseline. Usually, you can start with something much smaller than having the whole data set of everything that you ever collected. I would recommend to always start with a small subsample, start trying simple solutions on little data. last year, even though I said this in the homework, a lot of people complained, this takes like 10 minutes to run, so every time I have an error, I need to wait 10 minutes. No. You subsample it to 1% of the data, then you make your whole pipeline run. Once your pipeline runs, then you run it on the whole data set. So for prototyping, use subsamples of data, see what can you learn from small parts of the data. Don't invest too much upfront into a complex infrastructure. Also, even if you figure out, oh, adding more data helps more, you can probably still do it in a Jupyter notebook. So I've seen people use like Hadoop clusters when they had 100 gigabyte of data. 100 gigabyte of data is nothing on modern computers. Like this is an old slide, so you can get, it says you can easily get 512 gigabyte of RAM. Right now, I think you can get like 2 terabyte of RAM or something on EC2. And maybe the machine is a little bit more expensive, but the machine is much, much cheaper than all your time trying to set up some Spark cluster. All right. So this basically ends my overview of like the big picture of doing machine learning stuff. And I want to sort of summarize some of the things that I want to talk about in more depth in this course. So one thing that I really want to focus on is good software engineering practices in addition to good machine learning practices. I'll probably change some of the software engineering things compared to last year, but I still want to make sure that you have a good grasp of the software engineering tools. Machine learning systems are usually quite complex and hard to understand and hard to debug. So if your software development isn't really that great and your technology doesn't support you that much, you basically lose before you start. So even like deploying simple things is hard, as people from DevOps know. Like deploying simple solutions in a robust way is hard. But we're going to work on very complex solutions, possibly. And so it's very important that you have good software engineering practices. Another thing that I will keep talking about is problem definition and measures of success, because that's another thing that people often overlook over and over again, and no matter how often I say this, people still make the same mistakes. See what is it that you actually want to achieve, what is your actual goal, and establish a baseline for your actual goal. And then find a proxy that you can measure easily and see how well does your baseline perform, and then do anything else. First, think about what's the actual goal, and what is the proxy you can measure, and what is the baseline. The other things I really want to talk about in this course, or what I want you to take away from here, is things that are not really taught much in classical machine learning courses, which are like feature engineering and data cleaning, and how to select algorithms. You will see in the homeworks that a lot of your time will be spent in doing feature engineering and data cleaning. No data sets are ever clean, and I'll give you some homeworks with pretty like messy data, and you'll have to go through and figure out what to do with that. And we'll talk about this in class, obviously. And as I said, I always want to start with the most simple baseline, but beyond this baseline, you should think about what are the appropriate models for a given task. And we'll talk about this. And what are the strengths and weaknesses of different models. Finally, I really want to emphasize model selection best practices, because people often report overconfident results. They think their model is good when in reality it is not. And we'll talk a lot about how to evaluate the model in a realistic setting, and what the caveats are about assessing how good your model is. really what I want to emphasize is the whole workflow. Here's like one possible instantiation of the workflow, which is starts. Here it says user, but basically starts with your application. It starts with the thing you care about. From there on, you collect data. You probably analyze your data. You need to clean your data, do feature extraction, so on. Then there's a model building phase and the model evaluation phase. And there's usually an iteration. Here it's said between model building and model testing. Usually it also comes back to data cleaning, so you find out your data is too dirty for your model and so on. And so there's several feedback loops. And then there is the outermost loop of, well, I have a model now, I'm going to deploy it. How does it change my actual application? What is the practical outcome of this model if I deploy it? And then evaluate if this changes the process again. And this is, in a sense, a very simplified pipeline, because this doesn't illustrate any of the software development aspects. If you want to talk about the software development aspects, this is going to become a much more messy diagram. So I want to focus on both this whole machine learning workflow, but also talk about the software development workflow that goes hand in hand with it. And so this was sort of the high-level overview, and the things I want to talk about next are actually sort of going in the opposite direction, starting with software principles and general coding guidelines. Right, so until 25, right? Okay, let's see if we can get through this. Otherwise, we'll continue it next week. So I might be a little biased because I'm mostly a software developer, in a sense, but I think to be successful, as I said, in machine learning or as a data scientist, you have to have really good software engineering practices. And there's a couple of core principles in software engineering that I first want to go through. One is, there's two quotes I want to start with. This is one is by Harold Abelson, who's one of the authors of the Wizard book, which is basically about how programming languages work, and or how Lisp works in particular. And he says, programs must be written for people to read and only incidentally for machines to execute. So if you write any data analysis or any machine learning or anything, you should target it at a human reader. You shouldn't like mess around with it until it kind of works and does what you want. You write it down in a way that you can go back and understand what's happened, and your colleagues or your friends can go back and understand what happens, and possibly even your boss can go there and understand what happens. Another way of saying this is that programs are read much more often than they're written, and putting in a little bit of effort into the writing will help you a ton reading it later. Your old code will always come back to haunt you, even if it's just a class project. And so very often the person that reads it is your future self. And if it hasn't happened to you, it will happen to you, that going back to some code you wrote like 3 or 6 months ago and you have no idea what happened there. And so I really want you to focus on writing readable code. Part of this is emphasized again in this next quote, which is by Brian Kernighan, who wrote basically one of the style guides and tutorials on C programming. Everyone knows that debugging is twice as hard as writing a program in the first place. So if you're as clever as you can be when you write it, how will you ever debug it? This says, if you're clever, you're probably not clever enough to really understand what your code is doing. Don't try to be clever. In particular, even if you understand it now, you'll forget what the clever thing was that you did, and you'll forget in the future. And someone else reading the code will have no way of understanding what's happening. So don't try to be clever, try to be clear in whatever you write. Yeah, so future you is the most likely person to go back to this code and try to understand what's happening. And you really want to be nice to your future you. Oh, another thing that I really want to emphasize is avoid writing code at all costs. Some people that are software developers like, oh, writing code is fun, I want to write all the code. But what you should really think about, every line of code comes with a cost. In that, if you write it now, at some point later someone else has to understand it, has to maintain it, has to do something with it. Don't write code. Write as little code as possible. This goes back to, or this relates to what I said about complex models. Like, is it really worth deploying a more complex model if it will give you more trouble in the future? Is it really worth adding some functionality to your code that will make it 3 times as long and like 5% faster? It's every line of code you should think of as a future maintenance cost. So if you write a lot of code, don't be proud, be sad. All right, this was a very high-level overview. I'm just going to go a little bit over because I don't have that many slides anymore. So I want to talk a little bit about Python. So the whole class will be in Python, and I spend quite a lot of time writing Python code, and so I want to first talk about why I want to do this in Python, and then all the things that I really hate about Python, and the things that you should really should pay attention to when using Python. So why do I like Python? Or why do I teach this code in Python, maybe? So why do I teach this course in Python? So one of the things that's good is it's a general purpose language, which means you can do anything with it. This is particularly helpful because it helps you integrate with like web services. So a person that writes a web server is more likely to know Python than to know R. And so it's easier to integrate your data science or machine learning solution into existing systems. Also, or you can write a graphical user interface, even though that's something people don't really do these days anymore. Another reason why Python is great is there's lots of libraries that help you with a lot of the things. So as I said, we're not going to really write any algorithms. All the algorithms we're going to use are implemented like in scikit-learn or Keras or some other libraries. There's also lots of libraries to do more advanced probabilistic modeling, to do data visualization, and so on. And arguably, it's pretty easy to learn to use. I think in the data science space and the machine learning space, there's not really a lot of contenders. The only real contender I see is R. And you can probably also teach this class in R with like slightly different emphasis. I prefer, well, maybe it's like just an accident that I do Python instead of R, but in terms of software engineering practices, it's much harder to write good code in R, and also the tooling is worse in R. The statistics software is better in R, and so if you're doing statistical analysis, probably R is a better choice. If you want to write a production system, probably Python is a better choice. People use other languages for machine learning. I think one of the somewhat popular ones is Scala, but if you want to do some exploratory analysis, initial analysis, prototyping, it's a real pain in Scala from what I've done. And also the libraries are not as rich as they are in Python. And so I think Python gives you a good trade-off between like being able to easily do some interactive analysis and potentially also being able to be deployed. Clearly, if you're like Facebook or Google, you don't want to deploy a model in Python because there's going to be too much latency in most cases. But in many cases, Python is just fine. Yeah, so one of the reasons why I don't like Python is it's pretty slow. If you actually write things in Python, which has the consequence that none of the tools we use are actually written in Python. NumPy is written in C, SciPy is written in C and in Fortran, Pandas is written in Python and Python, and scikit-learn is written in Python and Python as well. And CPython, so the Python interpreter we're using, is written in C. This is a little bit annoying because it means if you implement something yourself in Python, it's sometimes going to be slow depending on how you write it. It also makes it a little bit harder to contribute to these libraries because if you really want to fix a bug in NumPy, you have to learn C. And that's a little bit annoying. So in this course, we're going to stay just on the Python side, and we're not going to try to do anything fancy in Python or C. But it's something you should keep in mind, that basically none of the tools are really written in Python. I had previously had a longer slide of Python 2 versus Python 3 and what are the differences. This year I can say, don't use Python 2. Always use Python 3. There's no reason for any of you to use Python 2. There are some companies that have big code bases in Python 2 for which there's some reason they haven't transitioned yet. But all the newest version of all the libraries like Matplotlib, NumPy, scikit-learn, they don't support Python 2 anymore. Don't use Python 2. Use Python probably 3.6 or 3.7. Another thing that's a little bit of a pain about Python is the package management. And yeah, that's sort of somewhat annoying, but it's something that you will have to deal with, so you should really learn about it. How do you install all the packages you need? One lesson that everybody here needs to learn is don't use your system Python. If you're, probably on all operating systems, these days they come with some Python installed. Don't use it, don't mess with it. You're gonna screw up your operating system, and you're gonna not have a fun time. Instead, use virtual environments. Either virtual env, which is like the native Python thing, or use conda. So for most people in this class, I would highly recommend you use conda and anaconda, which comes with all the packages you're going to need. And have a conda environment that's just for this class, for example, or just for machine learning, and make sure you understand how this environment works. You should also try to understand the interactions between conda and pip. Pip and conda are two package managers. Both are used for Python, and they don't mix. And if you try to mix them, things will go horribly wrong. They're a little bit better these days, but sometimes they can still go wrong. So pip is sort of the Python native thing, and conda is like something that works with compiled libraries better. If you install something with conda, don't upgrade it with pip. If you install something with pip, don't upgrade it with conda. If you do either of these, everything's going to break. I really like conda. I use it as much as possible. Some packages are not available on conda. Then I install them using pip. One of the things with pip is pip doesn't have dependency resolution. So if a package relies on a package that relies on a package, it's not going to install the third package. But conda does do that. So basically, if you don't want to deal with it, as much as possible, use conda environments. Be careful not to mix conda and pip. There's actually a nice write-up. Well, in addition to dealing with dependencies environments, you also have to deal probably with Jupyter kernels. We're going to use Jupyter extensively in the class, and I really highly recommend that you use Jupyter for your homeworks. Actually, I think I require that you use Jupyter for your homeworks. Scratch that. And so Jupyter has what's called kernels, which are sort of different environments in which you can launch anything. But they're not the same as environments. So there's a great blog post by my friend Jake Vanderplas, who also wrote the Python Data Science Handbook. And I really highly recommend you read this on how to manage environments and how to manage Jupyter kernels. Because we're a little bit over time, I don't want to talk to this in too much detail, but make sure that whatever kernel you're running corresponds to the environment you think you're running. There's like this change kernel, and this should list all your environments ideally. You can pick the environment that you have your tools installed. And if you come to my office hours and you use your system Python, I'm going to send you home again, by the way. If you don't use a virtual env for conda env, I'm not going to answer your questions. Also, don't go to the CAs. I tell them also to not answer your questions if you use your system Python. So this is sort of one part of the tooling that you need to understand. It's a little bit tricky, but this is something you will have to deal with. You will have to deal with this in your job, and probably at your job, you're going to be the expert in this. So really make sure you understand all this tooling. Another downside of using Python is that it's dynamically typed and interpreted. That means that actually you can have code running that somewhere has invalid syntax because it's in an if statement that never ran. And then sometime in production, this if statement runs and there's invalid syntax and everything falls down. Also, it means that code is less self-documenting because you don't have variable types. And these are things you should keep in mind and sort of guard against. One thing is that you should think about the editor you use and become friends with your editor. I really don't recommend using Notebook++, which is like the bare minimum. Find an editor that has Python integration, for example, VS Code, Sublime, Atom, PyCharm, whatever. You want to be able to use Flake8 and PyFlakes, which will check your code for syntax errors and has syntax checkers for you. Also, I really encourage you to write in PEP8 style, which is the standard style for Python. And there's also automatic checkers that you can have enabled in your editor. This will also make it much easier for the CAs to grade your assignment. If you already have code lying around, you can use AutoPEP8 to convert it to the standard style. But really, make sure you're friends with your editor and you understand how to use your editor and configure it for Python. All right, so that's it for today. Next time we'll talk a little bit more about some software engineering practices, and on Wednesday we're going to start with visualization.